I've had a lot of parents and even students concerned and questioning about how this ice cream cone method of division connects to the standard algorithm, or as they say it, the way my mom and dad showed me. And so I kind of want to help fill this misunderstanding and show the connections between the two models. And then that way you can kind of see the reasoning. So if we did an example, let's say 643 divided by, let's say 5. No, let's change that. Let's say 4. No. Let's say 7. Okay, so doing the ice cream cone way, we would write 7 times some number equals 643. And then we would roll our 7s. 7, 14, bop, bop, 21, 28, bop, bop, 35, 42, bop, bop, 49, 56, 63, 70, bop, bop. So when we do it the traditional algorithm way, or the standard algorithm way, we have the same problem over here. When you do this way, you first ask yourself, 7 times what number gets closest to 6? Well, 7 is larger than 6, so we know we're not looking at that anymore. So we would write 7 times 0 is 0. We would subtract and we would get 6. And then just because we know that we bring down, which is really like the unbundling step. So then we would ask ourselves, 7 times what number gets closest to 64? Well, I know 7 times 9 is 63. And I subtract and I get 1 left over. I'm going to pause right there with that part, and I want to come over here and show you the ice cream cone way. So we label our places. We ask ourselves, can we share 600 scoops with 7 cones? Well, we know 600s, when we're thinking about our base 10 blocks, 6 of those flats, we can't share that evenly with 7. We have to break it up. So you can see this directly correlates to this whole step right here. We can already see that when we're saying we have to break it up over here, that's like where we're writing times 0 and subtracting and then going to the next place value. Because you can see 64 is up there to begin with. So we ask ourselves, can we share 64 tens with 7 cones? Well, sure, of course we can. So I go through my numbers, 7, 14, bop, bop, 21, 28, bop, bop, 35, 42, 49, 56, 63, 70, bop, bop. Oops, I went too far. 7, 14, bop, bop, 21, 28, bop, bop, 35, 42, 49, 56, 63. So I had 9 fingers up. And I know I'm looking for 9 tens because that's in the tens place. So I write 7 times 9 tens, which is 90. And 7 times 90 is 630. Okay, so look over here. 7 times 9, but notice that when you're looking at this, this is ones, tens, hundreds. So 9 is in the tens place just because that's where you write it. So we did the same thing, 9 tens, which is right there. We got 64. Now here's where the standard algorithm doesn't really connect with the ice cream cone method, because this just says that we got 63. So the reason we're showing them in this ice cream cone way with the partial quotients and partial products is because they're understanding this is 63 tens. This just, to me, looks like 63. So we're really helping them understand the place value. So back over here to the standard algorithm. We have 1 left. Come back over here to the ice cream model. When we do 3 minus 0, we get 3. 4 minus 3 is 1. So we have 13 ones. Let's look over here. We have 1. We bring down the 3. We have 13 ones. Okay, so this part was from the subtracting, and we brought the 3 down. But over here we can see you're not bringing a number down. You're just taking away the number you decomposed and took apart. So we ask ourselves, can we share 110 with 7 cones? Well, no, that's not going to work. So can we share 13 ones with 7 cones? Well, sure. I would run through my numbers and I would see the biggest number I could do is 7. So that's my first number. So I write 7 times 1 equals 7. And when I subtract, I get 6. Over here, 7 times what number gets closest to 13? Well, 7 times 1 is 7. And when I subtract, I get 6. Over here, we know when you have a number left over and there's no other numbers to bring down right here, I know that that's my remainder. So this would be remainder 6. So 91, remainder 6. When I come over here, I add up my partial quotients. I add my scoop on top, so 90 plus 1 is 91. 6 is not enough for a scoop, so I add my cherry, whoop-de-doop. I can see my quotient is 91 remainder 6. Same thing as over here. So if you want to try to do this way, that's fine. However, you must also do the ice cream cone method first. So if you want to challenge yourself over this break, maybe see if you, once you do the ice cream cone method, see if you can try and solve them using the same standard algorithm way. So we divide first, 6 divided by 7. Then we multiply, 7 times 0 is 0. Then we subtracted right here. And then the next step is we bring down the number. So you literally just go divide, multiply, subtract, bring down. Divide, multiply, subtract, bring down. Until you get until where there's no other numbers to bring down. And if you can see the connection between these two, then that's totally fine. I want to go ahead and show one other way, one other example to connect the ice cream cone method with the standard algorithm. So let's say we have 406 divided by 3. Okay, well, I know with my ice cream cone method, 3 times something equals 406. And then I need to go ahead and roll my 3's. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. Let me go ahead and set up my standard algorithm over here. So remember, the steps are divide, multiply, subtract, bring down. There's a lot of sayings to help you remember these steps if you want to think of it as, does McDonald's serve burgers? Or you could even think of it as daddy, mommy, sister, brother. Whatever it is that helps you is great. So first we divide. Can we divide? 4 divided by 3. Well, that's kind of tricky to think of. Then you go to the multiplication step. So 3 times 1 is 3. Now notice, here's another part where the standard algorithm doesn't really help you understand place value, because this 1 is in the hundreds place, because ones, tens, hundreds. But really, I'm saying to myself 3 times 1 is 3, and that's really not what I'm doing. But I go ahead and get that. I'm going to come over here. Ones, tens, hundreds, the largest, so I ask myself, can I share 400s with 3 cones? Well, sure. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. Oops, I went too far. 3, so that's my first number, 3 times 1, and it's in the hundreds place. 3 times 100 is 300. So right here you can see a similarity with this, but you can also see a difference. I did do 3 times 1 is 3, but this is showing me it's actually 3 times 100 is 300. Then I need to subtract to see how many scoops are left. I get 106. Let's look over here. 4 minus 3 is 1. Then I know my next step. I subtracted, next I bring down. So I bring down the 0. Okay, so I can see the 1 and the 0 here, and the 6 is still up there. So this is kind of a spot where it changed a little, but come back over here and let's look. Ones, tens, hundreds. Can I share 100 with 3 cones? Well, no. Can I share 10 scoops with 3 cones? Sure. When I roll through my numbers, the closest I can get without going over is 9. And this is 1, 2, 3. So I do 3 times 3, but this is 10. So 3 times 3 tens, which is 30. 3 times 3 tens is 90. Let's come over here and look. So 3 times what number gets closest to 10? Well, 3 times 3 is 9. And I subtract and I get 1. Okay, well, let's come over here. 6 minus 0 is 6. 10 minus 9, or I could regroup if I need to. 10 minus 9 is 1. Well, I've got the 1. And look, my next step is bring down. So I see, look, there's the 16 I'm looking for. So 1s and 10s. Can I share 1 10 with 3 cones? No. Can I share 16 1s with 3 cones? Sure. Closest I can get without going over is right here. That's 1, 2, 3, 4, 5. So I do 3 times 5 equals 15. I subtract and I get 1. So I come over here. 3 times what number gets closest to 16? Well, 3 times 5 is 15. I subtract and I get 1. 1 is smaller than my divisor, so 1 is my remainder. So I got 135 remainder 1. Over here, when I add up my scoop, 100 plus 30 plus 5 is 135. 1 is not enough for a scoop, so I add a cherry. Oop-de-doop. So I can see that if I really looked at this very, very carefully, this is the hundreds place, this is the tens place, and this is the ones place. The only problem with the standard algorithm is that when you're reading it to yourself and you're doing the math, you're not actually realizing that these place values are what they are. We're thinking 3 times 1 is 3, but over here we can see it's actually 3 times 100 is 300.